This is Mrs. O'Neill for AP Chemistry, Chapter 6, Section 8, Electron Configurations. I'm going to go through most of this rather quickly because you should have learned this in Chem 1. So I'm going to remind you that as things get more difficult or things are not coming as easily as they can, you can always talk to me in class or before school or after school. So please come see me if some of these things, I'm assuming that they're more review for you, but you still might be struggling with the information. So that intro lesson on electron configuration you should have watched, and here are my notes. So we talked about how the electron configuration is just a distribution of electrons. In other words, where those electrons can be found in an atom. He also talked about ionization energy, and that's how much energy is needed to pull those electrons away from an atom. Gave you a nice flow chart as usual. So then he gave you hydrogen as an example that has one electron and one proton, but he also said you have to quantify this force between those electrons and protons. You have to quantify the force between those positive protons in the nucleus and those electrons negatively charged in those energy levels. And this is called Coulomb's law. I can never say his name, Coulomb's law, and we're going to talk about him more in detail. And I also have a poggle on this force of attraction, this quantifying this force between those electrons and protons. So again, he talked about the charges of +1 and -1 and how the distance or that radius also takes into account how far away are those electrons from that middle positive nucleus. So here we have hydrogen versus helium, and he talked about which one's going to have a higher first ionization energy. So I also want to remind you that however many electrons an atom has, that's how many ionization energies it has. So in other words, hydrogen here has only one electron, so it only has a first ionization energy. However, helium has two ionization energies, a first one and a second one. So between hydrogen and helium, which one has a higher ionization energy? Well, helium is going to, because it's a 2-on-2. It's a 2 positive in the nucleus attracted to the 2 negatives on the outside in the energy levels. And so that attraction between 2 against 2 is going to be stronger than a 1 against 1 in hydrogen, making that first ionization energy higher in helium. So then he said, well, how about helium and lithium? Well, now it's called the shielding effect. So helium actually has going to be a higher first ionization energy because when we're talking about valence electrons versus the core electrons. So for lithium, we have 2 electrons that are in the core on the inside and 1 on the outside, 1 electron valence on the outside. So what happens is this 1 valence electron, this lonely guy, is shielded from the attraction between those negatives and positive of the positive protons in the nucleus and those negative electrons that are the core electrons. So there's some shielding going on there. So lithium has 3 ionization energies. The very first one, it's 1 valence electron. See you later. We don't need you. But the 2 on the inside, those ionization energies are really going to be strong because they are going to be really close to the nucleus inside. So then he talked about lithium versus beryllium. And again, beryllium this time is going to have a higher first ionization energy because we have 4 electrons versus the 4 protons inside. Again, versus this lithium, lithium has a lot of shielding going on. There's more shielding effect of those 2 strong ones than just that one kind of lonely guy. They kind of don't care about him. See you later. So he talked about the patterns of first ionization energy and the periodic table and how those elements, decrease and increase. Again, you should have learned this in Chem 1. We will review this when we get to the periodic table chapter. So he kind of went through how those electrons fill up the energy levels or those orbitals as you go through the ionization energy. So he kind of compared hydrogen and helium and how now you have 2 in the same orbital. It's going to make it stronger. So again, we go to lithium, which is the 2s. Uh-oh, that's now filled, the 2s. But then we go to boron, and now we're going to the 3 orbitals in the 2p section. And again, notice how 1 electron is going into each orbital before we start pairing up. And there we have neon, and neon now has a nice filled second energy level. And then he continued on with sodium. So he also told you how there's a little bit of a shortcut as well, or to find your electron configuration using the periodic table. So you have your S area, your P block, your D area, and your F block. We want to remind you that the D block is always going to be 1 less than the main energy level, or that period number, and the F block is going to be 2 minus, or 2 less than the main energy level, or your period number. Okay, talked about the electron configuration and the diagonal rule. It's a nice little way of organizing and knowing which way or which S, P, D, or F is getting filled at what time. So then he gave you some nice examples of hydrogen and boron and neon, and now sodium. He also gave you what's called the condensed version. So there's a long form and also the condensed form. So hopefully you tried chlorine and silver on your own and you checked your answers. And again, if you're having trouble with this, that's what in-class bookwork and classwork is going to be for. So on to your notes packet. Your objective in this section is to learn that knowing these orbital energies, as well as some of those characteristics of electrons described by Hund's rule, allows us to determine how these electrons are distributed in an atom. In other words, the electron configurations. So again, pause the video and then play to hear my words. Fill in the blanks, obviously. And please, please, please read as you're writing. This is a lot of words to fill in, but make sure you're not just filling in those words, that you're also reading each of those sentences or statements as we go along. So by now you know that the electron configuration is just arrangement of those electrons and how they're distributed throughout the atom. And of course the most stable is the ground state, where those electrons are in its lowest energy level possible. And of course those orbitals are filled in increasing energy, where there's no more than 2 electrons per orbital. Okay, so think about it this way. Electrons fill orbitals like patrons finding seats on a bus. Each electron is going to sit by itself in an orbital until another electron is absolutely forced to double up. And remember, they're also picky. So you might want to think about it this way, that they want to sit with somebody in their opposite or their opposite spin, their opposite gender. So that's just a nice analogy on how to fill up those orbitals. So Hund's rule, he told us that electrons repel each other. So the lowest energy configuration for an atom is one in with the maximum number of unpaired electrons in that orbital. So in other words, 1 electron in each orbital before we start pairing up. So he gave you some examples here of what lithium would look like, what carbon would look like, what neon would look like, just to give you an example of how, again, we're going to fill in 1 electron in each of those orbitals before we start pairing up. So now, if we look at this, orbitals available to a hydrogen atom. So notice, technically, all of those orbitals are available to the hydrogen atom. However, when we put an electron in there, of course, they're going to start repelling each other. So now, look at those energies of the 3s versus the 3p and the 3d. Now, because we're adding electrons, those energies are going to shift a little bit. So I'm going to show you that one more time. Here's hydrogen. There's nothing going on in there. Those are all of the orbitals that are available. And at a first glance, right, we look at the 3s and the 3p and the 3d. They're all in the same energy level, right? Because we say they're all in the 3rd energy level. However, once we start putting electrons into our atom, now that 3s, the 3p, and the 3d, now they're going to shift a little bit in energies. So helium has 2 electrons, and so that's why we go by the diagonal rule. They're going to fill up according to the energy, and there is one in your notes, but just kind of show you, the 1 energy level has 1 S2, the 2 energy levels is going to have like 2 boxes, 3 energy levels is going to have 3, 4 energy levels is 4, 5 energy levels has 5, 6 has 6, and 7 has 7 technically, okay? So then if you use your arrows like it is in your notes, again, you're going to fill up according. Now that's kind of where we stop here because again, you kind of get little fishy here. I don't know how to say this, but they really don't have enough electrons yet to fill up those orbitals. So we're kind of done here at the 7p6 for now. But technically, you know, later on, you never know what's going to happen in the future and what they're going to find. But technically, you know, you would have 5 orbitals in the 5 energy levels. So we also want to remember again that your diagonal rule is being filled by increasing energy going down, right? So 1s has the least amount of energy versus your 7p has the most amount of energy. So here's yet another example of carbon, and I'm showing you this because we dealt with carbon in chapter 24 when we dealt with organic. So why does carbon do what it does? Well, let's fill up those electrons. We know that carbon has 6 electrons. 1, 2, 3, 4, 5, 6, okay? But now let's look at its Lewis dot diagram. So because the 2s is already paired, really our Lewis dot diagram should look like this according to that orbital diagram, a pair and then 2 singles. However, we know that carbon can bond 4 times. So since it needs 4 unpaired electrons in order to have 4 bonds, we actually have to take that 1 electron and it's going to move to the side there, making 4 evenly energy electrons, if that makes sense, hopefully, right? So if we go back, just going to go real quick back, the amount of energy in the 2s is going to be different than the 2p. However, because we know that carbon can bond 4 times, we know that that electron is actually going to move down to make 4 equal energies of those electrons. And that's why carbon can bond 4 times. Kind of pretty neat. And again, not all elements do this, but it does happen for carbon. So even though we should have a pair and 2 singles, we know that carbon bonds 4 times. So here are some thoughts. Elements in the same group are going to have the same configuration because they have similar properties. Think about those noble gases. They have that filled outside energy level. And of course, the condensed electron configuration. You just take that noble gas configuration and then the rest of the electrons. So you can kind of replace part of the long configuration with that noble gas. So here's some examples. You might want to pause and see if you can do the entire configuration for neon and aluminum in its ground state. Hopefully you got that. And hopefully you got that. Okay, but notice aluminum is going to be very similar to neon with the 1s2, the 2s2, the 2p6. So we can actually condense that, and I believe that's where we're going to next. So aluminum in its ground state condensed would basically be neon 3s2, 3p1, whatever's left over. So hopefully that makes sense to you. So what would aluminum be, though, in the excited state? So let's look at that condensed, and now let's make that an excited state of aluminum electron configuration. We're going to do this. We're going to take that 3p, and it's going to jump up to another energy level. Okay, so you might see it this way, and sometimes you just see like the one of the electrons from the s going to the p. So as long as you see that there's the same amount of electrons, but just one is being shifted somewhere else. Okay, so if we look at this first, my first question is going to be, is this electron configuration a ground state configuration or an excited configuration? Hopefully you figured out that it was excited. And again, the reason why is you don't have a filled 4s1 electron orbital here, right? The 4s should be a 4s2, but that 1 must have moved to the 3d. Now, my next question is, what element is this? Before you go any further, I'm going to tell you always, always, always count those electrons. So 2 plus 2 plus 6 plus 2 plus 6 plus 1 plus 6 should give you the amount of electrons for manganese, Mn. So just count those electrons. So there are 2 types of electrons that I talked about before, your core and your valence, inners and outers. And again, going through another example for tin, which has 50 electrons, just kind of going through what that would look like in its condensed form. Also, there's some exceptions, and those exceptions you should know. Real quick, there's some others.